Software engineering, well, the short definition is the engineering of software.
Software engineering is the discipline that applies computer science and engineering principle in a systematic and disciplined way in order to design, build, operate, and maintain large software systems.
My field of research is software quality in general, and more precisely software testing. In a nutshell, how can we make sure that the software is doing what it is supposed to do?
My research area is mainly concerned with verification and validation of non-functional properties of software, such as performance, schedulability, security, safety.
My research is in the area of modeling and simulation and real-time embedded systems, something that has been recently called cyber-physical systems. Basically, what we're trying to do is to build applications in which we mimic what happens in the real world.
Since software is more complex and plays a more important role, this brings new challenges to the software process and the methods that are used for building and operating the software.
One main challenge in software engineering and in the IT field in general is that we have very little data that engineers can use to decide in context whether to use one technology or another.
We want to run so many of these simulations in distributed fashion, in the cloud. So how do we integrate models in these distributed systems in such a way that when we put them together, they make sense and they run properly? And another major issue is repeatability of the simulation models.
Well, software engineering is everywhere. Every device like this camera, like my phone, my watch, has a little bit of software, and each time there is a little bit of software engineering involved.
We can think about e-commerce systems to e-government systems. For instance, the programs that allow us to submit our taxes, e-health field, smart cities. Let's think about buses and their schedule, smart homes.
So we use modeling and simulation everywhere in the world right now. It's one of the basic pillars of science and technology. You use simulation for control of traffic lights in cities. It's used for a wide variety of applications, ranging from protocols in networks, building software for your cars, up to aerospace engineering.
One of my main activities is to use empirical studies to give empirical data to the software tester so that she can decide in context whether to use a specific testing technique or another one. Again, there are very little empirical data about that. I'm trying to fill the gap.
I participated in a working group of the object management group, which defined two software standards.
Dr. Petriu is a contributor to two software standards for real-time systems adopted by the Object Management Group. These include the UML Profile for Schedulability, Performance, and Time in 2002, and the UML Profile for Modeling and Analysis of Real-Time Systems in 2009.
Those two standards allow to extend software design models in UML with performance, schedulability, security, safety information, and those extended models can be used to derive automatically software analysis models for the verification of the non-functional properties.
We have defined a series of new methods for modeling and their associated methods for simulating those models. We have created new algorithms that make that simulation to run faster, in an effective manner, cheaper, in distributed fashion. We have used this for a wide variety of applications. Some of the most recent ones are in the area of crowd modeling. So with the LRT construction downtown, what we have done is to model the effect of an LRT station in the crowds coming into a building downtown, up to networking protocols for LTE networks that ended up patented by Ericsson and a group of our students. Right now, the world is distributed. What I expect to see is that those models will be deployed in a wide variety of devices, ranging from your smartwatch, your camera, your car, and your bicycle. Modeling and simulation can provide the users with advanced methods for prediction that they don't exist today.
In 10 to 20 years, or maybe 30 years or more, I imagine that there will be more and more empirical data so that engineers can decide in context what is right and what is wrong with a better body of knowledge.